Good afternoon, everyone. How are we going? We're in week 7. We're back from our flexibility week. Uh, um, Someone said, "Holy heck, where did the time go?" Yeah. So the break is over. If you were taking a break, like I know that a lot of the time we end up working on things during breaks. Um, a lot of courses will probably still have had assignments running over the break. We sort of did, but not like I think low pressure end of the assignment. Kaichi said post lockdown haircut. Yes, Sydney has pretty much, not entirely, like only for fully vaccinated people come out of lockdown. Luckily, both myself and my hairdresser are fully vaccinated, so I got the sides shaved off my head again, which is nice. Okay, so I want to open with a video to, let's see if I get another copyright strike. I don't think I will, because I think this one's a promo video that's intended for people to watch. It's not actually that new. It's 2018, so this is, but I think this is important because this video is the thing that um, sparked a new method of rendering in graphics, and so I thought it'd be cool to watch. Lecturer reacts to Unreal promo videos. Turn off subtitles.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector.
So,
if you ask me,
this is real time right now.
This place should be transferred to Hoth. What? What?
Look at that. Look at those lights. Moving lights. It's so good.
You think she heard us?
Yeah, I think she heard us.
At least we blend in for once.
I like the humor in it. Like, stormtroopers always kind of make me laugh. Oh wait, let's go back to the start of the. That said start slideshow. I assume that means start presentation. They've changed the names of one of the buttons. So we're going to talk a little bit about this today, this buzzword that is ray tracing, that goes around a lot, and it's one method that we can use to calculate how much light there is in a scene, what the kind of, I guess what you'd call the global illumination, a lot of people will call it that as well, but that's 2018 there, and that is the video that I think heralded the current sort of batch of work in advanced lighting in computer games. I say computer games specifically because this is real time. Film's been doing it for years, but this was the kind of first moment that that we can see that this method called ray tracing was being done in real time. I'm going to talk about what this method actually is. I actually threw in a couple of slides about it because I knew people were interested in it, and it actually does help us a lot with the theory of what we're going to talk about today. And the main focus of the lecture today is light and lighting. You can see it's actually very interesting lighting on my face right now. It's dark in my room there. Maybe I should make it a bit brighter. Oops. Wrong way on my blinds. Now it's really, really bright. And it's glary. I mean, there was a possibility that if we wanted to do, say, 2 years worth of lecturing from home, that we would have set up some kind of studio, but I've still got like a temporary setup, which always feels like it's just here temporarily until we come out of lockdown. We've come in and out of lockdown multiple times, and I'm still teaching in the same spot. Okay, let's get into the lecture itself. All right, what did we learn before the break? So, remember back in week 5, you may not remember anything from then because it was such a long time ago. But even like talking about weeks 1 through to 5, we've been talking about all this stuff about how to get us to the point of having 3D geometry functioning in a virtual environment. But week 5 in particular, we looked a lot deeper at the reasons why we might want to have graphics at all. you know. And the whole idea, when we come back to it, graphics is for humans. Very, very, very much so. That if you were to give graphics to a machine to look at, it wouldn't entirely make sense. But there's so many things in graphics that are just entirely made to trick the human eyes and the human imagination into believing things. And so we went into a lot of that stuff. Like, what does design mean? Like, what do we mean when we're talking game design and narrative design and things? And how does that lead to us needing to make graphics engines in order to work for people? Because nearly all graphics engines have been built with this purpose of thinking that we need to see something, you know, at some point we need to see something, and that thing must be believable. So is it believable because we have been able to replicate the real world in such a way so that the expectations for movement and light and colors and things like that are met? We meet the humans' expectations, and that's the realism side of computer graphics, and that's driven so much of our rendering. But the other side of it is like, what about just pure stylism? Is computer graphics considered an art form? You know, there's so much stuff we can do with computers which we would consider to be super creative art that isn't necessarily grounded in reality in any way. Just as interesting. I find them both incredibly interesting. Like, realism is this kind of finite goal. It's really interesting because once you can convince people that something is real, like we look at deep fakes and stuff, you know, they're still early, but they're on their way. And we're going to get to the point where at some point in the near future, like I'm assuming within our lifetimes, we're going to have Hollywood stars who aren't human. So we're going to have genuine Hollywood stars who do not have a human presence, and their performance is entirely artificial. I don't know when, and I don't know how, and I'm sure there's going to be a huge kind of like controversy around this when it happens, but I think it'll be interesting to see nonetheless. And so we're talking about this kind of thing, and like, if we're talking about graphics and melding graphics with a field like AI, that's where it goes. You know, so I think that's really interesting. And we talked about the art pipeline as well, and we delved into the details when it got technical. You know, like I'm not going to teach you about concept art. That it's its own field, and you could spend years learning about that. But the assumption for this course is that none of us have any knowledge in that, so I'm not gonna kind of push that other than to tell you about it and that it exists and that it's, you know, without it we don't get the 3D models that we want. But later on in the art pipeline, when we get to things that are more computer specific, because this is of course a computing course, we looked at modeling and animation. So a lot of the details of how you end up with a whole bunch of verts and triangles and how they work, how you might move these things around, how they might move around in terms of manageable forms. So when talking about skeletal animation, we can have, I don't know, 100,000 verts in a model. That's pretty expensive model, but you know, it happens. If we had 100,000 verts in a model, we can't expect an animator to move 100,000 verts. It's so like, you know, it's so much effort, you know, so much manual effort to move them, and you can't expect someone to just sort of click and drag and select an arm worth of verts and just twist them and make it work. So that's why we do skeletal animation. We have the idea that the mesh, the outer surface, is attached to the inner surface, and inner pieces, and those inner pieces, there's less of them and it's easier to work with them. So looking into that kind of thing, and then that boils down really closely to what we've been learning about things like scene graphs and stuff like that. So the skeleton inside a model can really be considered the scene graph of a model, but instead of each object of the model being a single piece, these vertices are just kind of partially mapped to the bones, so that you get, when an arm moves, the triangles on, say, the top of the shoulder actually stretch and morph and change shape and stuff. So it's really interesting, really cool stuff. Just checking chat. Enterprise software, my streaming setup. Everything's temporary and then it becomes permanent. Ever hear of a language called JavaScript? This is all hearsay. I don't really know it that well, but what I heard, the story of JavaScript is that it was made to just fill a gap temporarily, and then 20 years later it's still around. Okay, so let's kick off something, and this is big. This is the biggest single topic of the course, I would say, and it's going to be stretched over 3 lectures, 2, 3 lectures, it depends. I'm not going to rush this. I have more slides today than I think I will get through, but I don't want to rush it. And I do want to do this in great detail. So what I'm expecting actually is a significant part of the final kind of third or quarter of this lecture will just spill over into Wednesday. And I don't have a good way to kind of separate this into chapters. So it's kind of going to be like today and Wednesday are one long lecture, because I don't want to split up this topic, but I have no choice. It just doesn't fit in 2 hours. So what we're going to talk about is, like, what is light? You know, we're not going to go into too much detail. I've already talked about this a little bit. I've talked about human eyes and things like that. And I really want to remain in that context. I think it's important for us to remember that everything we're doing with computer graphics is to get us to the point where we can look at the room that we're in and we can see objects and things. And then we look at our monitor and we see a 2D representation of the same idea of these objects, right? And we should get the same kind of result. We should get the same kind of believability. And one of the things that gets us really understanding that is a like amazingly intuitive idea of how light works. Like, we have been around light so much. And I apologize, I don't actually know if there's anyone in the course who is vision impaired in any way. I apologize to anyone who's vision impaired, because this is all very, very much based on people with working vision. I mean, if you have color blindness, you can still get away with nearly everything in things like computer games and films and stuff like that. I think people are careful to make things so that the most common, like red-green color blindness, can just watch everything fine. You know, you don't have really specific issues like that. But if you've got more kinds of vision impairment, it's going to be very difficult. So, because I'm going to be using examples for things that, like, from people who can see well. So, I apologize, because I think that graphics is very, very much based on people with working vision. So anyway, we're going to talk about this idea. What is the difference between the way light works in the real world versus the way light works in a simulation? And then we're going to talk about the fact that we have specific processing capability, to do things, and how we're going to use that, and what compromises are we going to make on our lighting to make it sort of genuinely work, in a sense. So we're going to start on a lighting system for polygon rendering, and it's a system called Phong lighting. We're going to add something to the Phong lighting later, but, you know, I'm going to build it up slow, right? You know, like little bits and pieces of lighting, and how we're going to approximate a real simulation model. So the first thing we're going to show you is the idea of a simulation model, which is what we just watched then in the video, and that's called ray tracing. But we're not gonna implement it, maybe. But I'm going to show you what is a more common form of lighting in polygon rendering that is used more commonly in a lot of the games and things that we're doing, and it forms the kind of fundamental basis to build all of these complicated and interesting lighting models, like things that we call deferred rendering, and other things like ambient occlusion and shadows and all that kind of stuff, kind of build out of the same system. So, I like my title slide sometimes. The title slide is light. Now, it's interesting, because light is something that the majority of us are inherently familiar with. If you get the joke, let me know. What is light? Or what is the light, if you will? Yeah, if you don't get the joke, it's okay. This is an image from Destiny 2, the computer game. Anyway, I'm not going to explain it. If you get it, you get it. If not, you can look it up. It's cool. It's a fun game. I haven't played it for years, actually. I fired it up again recently because I thought this would be cool to play in this course, to show you kind of like modern day advanced graphics. But I actually picked a different game. That'll be on Wednesday. But it's such an overly complicated game. I had no idea what was going on in it. Okay, let's talk about light. The physics of real-world light are important to us because if we want to simulate something, we must understand it, right? And the greatest thing about this is that I don't really have to explain it that much. I'm going to break it down and talk about it scientifically and things like that, but you can see it. Like, you can just look around and see it. You can see the effects of light already. And you have an assumption that light will do something, right? And because of this assumption that light will do something, it creates an expectation that if we are going to create something with computer graphics, it must behave in a similar way. And if it doesn't behave in a similar way, there's going to be a problem. People are going to start to reject the visuals that you're showing them if the light doesn't appear accurate in some way. So whether it's a simple simulation that's still mildly accurate, or whether it has to have a kind of a perfection for believability and things, it's really funny because I'm just looking around my room here and just going, man, the lighting's really good in here. Look at all these soft shadows and stuff. Like, this takes so much processing power. And so whatever processor is running the world that we call the real world, it must be super, super powerful. So for all of us to be interacting with it in real time like this, and you can't even tell what the frame rate is because it never drops. It's pretty amazing. People are talking about Destiny 2. Yeah, I don't know. I haven't played it in ages. I hopped back in because I thought, oh, let's play something like this to show people. And then I was like, I don't understand what's happening. So I hopped back out again and just uninstalled it. I was like, I can't do it. Okay, so in the real world, light is made up of these particles called photons. And there's lots and lots of these photons, and they fly through space in a sense, and they bounce off things. They're considered to be both a particle in that they can move and bounce off things, but also a wave in that they're affected by things like wave patterns and things like that. They have a wavelength, so the particles kind of like the particles oscillating in a sense as it moves through space. It's not really thought of as an actual particle. I think it's thought of as this weird amalgamation of them, because it doesn't tend to stop when it hits physical objects. So things like glass and stuff, it can move straight through them and things, but it will bounce off other objects, not based on whether the objects are solid or not, but based on whether the things are reflective or not. So it's interesting. The idea of light. It is an electromagnetic radiation. So as in, yeah, it's on the electromagnetic spectrum, along with stuff like microwaves, stuff like radio waves and things like that. And they behave very similarly. It's just a particular spectrum of it. So it's really funny when you think about like radio antennas and things like that, or you think about your mobile phone and things like that. All of those things communicate via electromagnetic radiation. So your Wi-Fi is sending and receiving electromagnetic radiation. We actually have electromagnetic radiation antennas in our head. These two eyes that are actually picking up certain spectrums of electromagnetic radiation, so certain wavelengths. So it's interesting because a UV is just above what we can see, infrared's just below what we can see, and it's really funny because infrared is what heat gives off, and UV is just another form of radiation, but like even mildly dangerous to humans, but like we can detect a certain small spectrum over the overall spectrum. So like when we talk about radiation, we think about like damaging radiation like X-rays, or like the radiation alpha, beta, and gamma radiation that comes off stuff like uranium and things like that, right? It's actually all the same stuff, but just different wavelengths have different effects. So it travels in straight lines, and it's basically instantaneous. Like, that's all I'm gonna say. I don't want to go into the details of this. I don't actually care about being correct on this, because the thing that's most important is how we perceive it. So we don't notice that light actually takes time to move. If you think about it in a particular way, the distance from the sun to the earth, the sun is the basic source of light. You know, it is the most common source of light that we're ever going to see. We will generally see in our lifetime more photons from the sun than from any other source. I hope. I know a lot of you are gamers. You may not see the sun very often. But I hope that you will get photons more from the sun than from anything else. So, it takes 8 minutes for a photon to reach us here on Earth, or approximately, from the sun. It depends on where we are in our orbit. Again, details not too worried about. So that is a stupendous distance. It takes less than a second for a photon. Like if a photon was to travel around the entire Earth, it would take less than a second to go that entire distance. So it's not something that we care about in this course. We're going to say it's effectively instantaneous. So we're going to say that a beam of light is going to travel entirely through our scene in a frame, which kind of works, you know, because even at the speed of light, a beam's going to, if we're doing it 144 frames a second, a beam of light's going to get through most of the scenes that we could make in graphics in that entire frame. The other thing about light is it reflects off surfaces. So when light hits a surface, the only reason we can see a surface at all, so like anything around me, like my face or like your monitors, anything like that, Tongju, my RGB keyboard gives me my daily dose of photons. Yeah, I know the feeling. The only reason we can see anything is because photons bounce off it. Right, there's no such thing as like a solid substance. I mean, there's some that create their own photons that come out, like, you know, the filament of a light bulb and stuff like that. But most of the time, everything that we're going to see, the only reason we can detect objects around us with our vision is because photons have bounced off them and ended up in our eyes. So that's the idea, is the light reflects off surfaces. So we see different wavelengths of light. I'm going on a funny thing here with the images where I'm not actually using proper scientific images, but I'm just using references instead. But what we're going to see is a mix of different wavelengths of light. So white light is generally thought of, you can break it apart using a prism like this. This is how you get like a rainbow. You can do it with a piece of glass, actually. I think if I could get this cup to shine the light directly from my light there, it would actually be able to split it up. But, you know, it's not a physics course, not super important, but the idea is any light that we get's made up of multiple different colors. So it has lots and lots of different colors that hit a surface, and different surfaces are going to do different things with those colors. So for example, my t-shirt here has yellow and red on it. The yellow sections are sections that are absorbing most of the different wavelengths of light. So it's absorbing the purple, well, I could call them the correct terms, like magenta, cyan, and green, and it's absorbing the red and the orange as well, but it's reflecting the yellow. So all these colors of light from, I don't know, the color from outside my window is vaguely white. It's not exactly white, it's got lots of different colors, but it's coming in, it's hitting my t-shirt. My t-shirt, where it's yellow here, is absorbing all of the colors except for the yellow, and then the yellow is bouncing off. You can see this from multiple different directions, which means when the light hits this, the yellow is bouncing off in like a spray of photons in any direction. And that's actually the difference between something that is like a reflective, like a shiny surface, versus something that is like a matte finish surface or a rough surface. A rough surface just bounces photons randomly. Whereas a shiny surface tends to reflect the photons exactly the direction they came in. So that's why you can see reflections in certain things, because the photons retain their kind of directional order when they bounce off something. Plenty of surfaces are going to be partially reflective as well. Like most glass is partially reflective, partially transparent, right? So what we see is going to be based on the materials in the surfaces that we're looking at, the amount and direction of the light that has hit it, and the colors of the light as well. So there's a whole bunch of stuff that's happening. Our eyes, I've talked to you about eyes before. We've got three different receptors in our eyes, these rods and cones that I talked about. Again, not a biology course, not going to go into too much detail, but the key thing is we can detect an amount of red, an amount of blue, and an amount of green, and that allows us to see different parts of this spectrum, and even the wavelengths in between the other wavelengths, because they will hit our receptors at a partial amount. So it's pretty handy. We've got, you know, the eye is an amazing thing, and its ability to deal with all these different colors is really good. Okay, so what we're getting is we're starting to put together the details of how light works in the real world so we can simulate it. So we're talking about particle waves, like they're kind of both, that will move through space fast enough that we don't really detect they're moving. We feel like they're instantaneous. They move in straight lines. They bounce off objects. If those bounces make it into our eyes can tell what they are, and so that's how we're detecting what we're seeing. So let's come up with a model for simulating light based on the real physics of light. So what we can do is we can have light sources in our scene. So I'm introducing now a new object in graphics, which is something that emits light. For the moment, everything we've done in graphics is just to assume that objects are whatever color they are. So there's just this blanket of light across the scene, but it's not directional. It doesn't cast any shadows. It doesn't come from anywhere. It's like every object just kind of has the colors it has. Whereas if you think about in the real world, if every object has colors but there's no light entering the scene, then you can't see anything, right? If there's no photons bouncing around, then we can't see anything. So what we're going to do is have light sources, and we're going to have these light sources send out photons or rays of light. I'm starting to use the terminology because this is like what we call ray casting. So we cast rays from our light source, for example, and we can say if we want to simulate roughly the same amount of photons that there are in the real world, we're going to kind of need billions of these for every pixel on the screen, because that's about the number, like roughly. They've actually measured the number of photons. So we have a rough idea of how many photons are being generated by our computer monitor. It's in the billions. I didn't bother really calculating this because I think it depends on, you know, how big the pixels are on your screen and stuff like that. But, you know, rough numbers, billions of these photons. So if we wanted to simulate a light scene, we know our light sources, like say this lamp that I've got here. That's great. Ooh, HDR. Anyway, more graphics buzzwords. I'm going to try to limit the number of graphics buzzwords I show you at one time. We've got one today, which is ray tracing. So billions of photons go out in every direction from the light source, or from whichever direction the light source may be pointed, whatever. Like when we consider the sun, all the photons are coming at us from roughly the direction of the sun, in a sense. They then bounce off objects. So if the photon bounces off an object, then we can see it. So we flood the scene with photons from these light sources and bounce off those objects. But that's not the only way the light works. Photons don't just stop after one bounce. They bounce off an object, they hit another object. Heaps of objects are going to be lit not by any kind of direct light. So there isn't necessarily a light source aimed directly at them. So this is the idea that things in shadow are still visible. So anything that's in shadow is not getting the first bounce of the photon, it's getting the second bounce, third bounce, fourth bounce of the photon. As these photons just bounce around, like my room here, it's kind of interesting, right? Because it's my light's off up there, but the light is just filtering in from the window. None of that's actually direct sunlight, because the sun is currently that way somewhere, but I'm just getting this bounced light here. So it's bouncing off just the parts of the atmosphere, bouncing off the trees and the other houses and stuff nearby, all that kind of stuff. So what we're getting is this idea that the light is just sort of filtering through from things. So what we would need to do to simulate this is for every ray of light that we've sent out, every time it hits an object, it's going to bounce off into multiple other photons. And so all those multiple bounces are going to have less intensity than the original because they're splitting up where the photons are, and they will do that again and again and again and again. And if you just bounce these things around the scene enough times, you will get an accurate simulation of what the light is. And then if we want to detect whether we can actually see something or not, we can have a camera in the scene. Now, we've placed cameras in the scene already, and then we've mathematically determined which objects are visible. Now, instead of mathematically determining which objects are visible, we would look at these rays that are bouncing around the scene and go, hey, there's a ray that went straight through one of the pixels and to the camera. So we'd have a near plane and the camera, and we'd say any photon that manages to pierce through that near plane and hit the camera is something that is visible. So that's light in exactly the same way our eyes are doing it. The photons bounced around, you know, these things had billions and billions of kilometers journeys through the universe coming from the sun. I mean, the one coming from this lamp hasn't. The photons from this lamp have had a very, very short journey. They've been generated here and they've come straight in to my eye, at which point they are consumed, reflected, or consumed. I don't know. Absorbed, I think, is the better word for it. Consumed. So, if one of those rays passes through one of the pixels in our near plane, so we could separate our near plane into a grid of pixels, and hits the camera, then we say, okay, that is what the camera sees at that point, in the same way that if a photon reached our eye after reflecting off objects, that's what we'd see. And so that's what color the pixel is. And so this would end up being like an accurate way to simulate light. I drew a picture of it. I was going to draw the picture live, and I thought, no, that's 10 minutes. You don't need to watch me fumbling with Microsoft Paint. So we've got our light source here. I've drawn this little sun, and here's two of the rays hitting this kind of scene. So we've got a cube here and a green floor or like grass or whatever, you know. It's not really that important what it is, but every time it hits one of these objects, the rays are bouncing off in multiple different directions. And we've got a bounce here. I didn't do too many because there's so many. But the light hits this object, bounces and hits this object, and then there's less light, but there's still light happening. And there's a few of these rays that have bounced off these particular objects and passed into the camera in the right position, right? So if they have bounced off those objects into the camera in the right position, what we get is there is a certain amount of color in that position in our view. And so this is a model that makes perfect sense because it is a simulation of real world physics. And we can use it because it's a simulation of real world physics. You can already tell by the way I'm talking that this might not be what we actually do. Because a lot of the time when I set up an example, it's to bring you to the example we're going to use rather than the real thing. But okay, so we've got this idea. And if we send out enough of these rays of light from this light source, this is going to be able to build up this picture. So technique makes sense, right? It's an accurate simulation of real light. If we can just do enough of these, we're going to get a very good idea of how the scene is lit. There's nothing super complicated about that. You send things off in random directions, so you could just pick a random vector from your light source. If our light source is just a point in space, we can do that, right? Or if it's the sun's really far away, so they're all coming in the same direction. We just get a lot of these things, hit things in our scene and bounce them off. And we bounce them off depending on what the things in our scene were. So you can see that the light, when it hit the blue object, was mostly blue still when it bounced off. When it hit the green object, it was green light that bounced off, right? So we would do those mechanics of absorbing and reflecting only certain colors from things. What we get out of this is we get realistic shadows, we'd get realistic reflections, because every shadow would be cast based on the light hitting things and not being able to go through. So yeah, this is good, right? This is going to work. And I say, wait, did you say billions? Yeah, billions. Okay, so we've got a problem there already. Billions means computationally extremely expensive. If you want an accurate look at this in the same way that you'd get light acting in the real world, the amount of simulation necessary to detect where all of these photons have gone, and every photon, if we can count them as single photons, which is not true, they're not. They don't go. I mean, I guess if it gets dark enough, yeah, a single photon moves through space, but they tend to move together in these massive packs of billions of them, right? And then when they hit something, they bounce off in lots of different directions, and that ratio of what they bounce off in different ways is how they split up into pieces. But we would probably be like, okay, single ray splits into multiple rays of lower intensity. Those lower intensity rays hit something else, and then they split into multiple rays of lower intensity. You've got this kind of conservation of energy thing happening here, where, yes, some stuff is going to be absorbed on the bounce off surfaces, but other things are definitely going to come off as a percentage of the initial intensity in all different directions, right? So this is going to be very computationally expensive to track all of these things and to decide how many bounces you're going to need for each ray of light until it reduces itself below a threshold that you're like, okay, too dark now, don't need to keep tracking that bounce. But if you do end up in a situation where you're not tracking the bounce anymore, then what are you going to do if an object is really dark? And you should be able to see it in another direction, right? So it's just like, yeah, really full on. Okay, so very computationally expensive. Not only is just tracking those things bouncing around computationally expensive, collision detection is also computationally expensive. So if we want to find out whether one of these rays has hit an object or not, that's a fair bit of work. So we'd have to say, this thing passes through the scene. We have to test it against every triangle in the scene to see which triangle it hits. And it's like, what? It's like, how do you deal with that? How do you limit that? And it's very difficult, right? So I'm not going to go into too much detail. Somewhere, if we want to do like a full physics simulation, then we'd spend like, 2 weeks on collision detection in the same way that we're spending 2 weeks on lighting, because this is a graphics course. On top of all of this computation being incredibly expensive, most of it is not even used. So the only calculation that we actually need is the rays that end up at the end of all of their bounces hitting the eye or the camera. So everything that bounces around the scene and doesn't hit the eye or the camera is actually wasted. We don't use it at all. So it's awkward because you do need to send all these billions of photons in every direction. Because if you don't send them in every direction, you don't capture those bounces off to other directions and other objects and things. But if you are going to have them bouncing off things in the correct ratio, then you're going to end up wasting a whole bunch of them. But you still need to track where they go, because you don't know if off the next bounce or the next bounce it ends up bouncing into the eye. So very, very expensive. Funnily enough, this technique called ray tracing was thought to be infeasible. So up until pretty close to 2018, people considered it a theoretical possibility, usable in some ways, but not usable in real-time graphics. And so this is why this is super, super current. We're talking about this, that in 2018, when this came out, and they were like, we're doing this in real time. So NVIDIA and Unreal and DirectX, actually, which is one of the other, like OpenGL is one of the graphics libraries, and DirectX is the Windows graphics library. So these three companies got together and said, all right, let's do it. Let's do this ray tracing thing. And so they did it, and it actually became commercially available in 2018. So this is the RTX series of NVIDIA hardware cards were capable of doing this, and I think it's DirectX 12. I wanted to say 11. I haven't actually looked that up, but I think it's either 11 or 12. Started being able to do this, and so that's very interesting. However, it's still not used very much yet, and it still is very, very computationally expensive. So it's still taking up all our graphics hardware to do. So it's kind of like, yeah, everything that I said about it being difficult is still true. Like we haven't reached a magical point where like we've made a better algorithm that makes it easier to do. There are other algorithms that get close, actually, that don't cost as much. Like there's a technique called path tracing, which is slightly different. And these kinds of things have been used in movies since the 90s. So we're talking about like late kind of Toy Story era. I think the Cars movie from Pixar was one of the first ones to have a form of ray tracing used for the majority of the movie. So the big difference is, right, so I'm just talking about this thing, and the only reason we don't use this is it's computationally limited. So the fact that we just don't have enough mathematics calculations in our graphics card to do this. Or we do now. If you've got a RTX series graphics card, so the RTX 200s or 300s series can do this. They just don't necessarily do it that fast. So yeah, it's here and it's capable. But the difference is that if we're trying to do ray tracing in games, then we're looking at trying to do this with a budget of 1/60th of a second or 144th of a second. That's tough. Like, I think like trying to do ray tracing at 144 frames per second, you're gonna need some really beefy hardware to do that. And someone else has already bought that hardware to mine Bitcoin, so you know you're not even gonna get it. Okay, so but the interesting thing is like film has an average, not necessarily like always the same, but an average of 8 minutes a frame. When you've got 8 minutes a frame, these techniques become feasible, right? So were feasible in the 90s, right? And they were using these kinds of things in the 90s through to the present day to do a lot of things like reflections, soft shadowing, and stuff like that. So they were already using these things called Monte Carlo methods to approximate lighting, where you send out a Monte Carlo method is a mathematical method of sending out a whole bunch of possible data and then seeing where they hit. And if your data spread is reasonably random enough, Monte Carlo is a casino, so it's about randomized algorithms. If your spread is random enough, you get an idea. There's an interesting thing you can do as an experiment with that is like calculate the value of pi by throwing random XY coordinates at a circle and seeing which things are inside or outside the circle. The more of them you do, the more accurate you get. So it's that kind of thing. Ray tracing is the same thing. The more photons you send out into the world, the more accurate your lighting is going to be. But for it to be human believable, it's got to get into the billions. So that's the messy thing. Alcinio is asking about path tracing. I don't know that much about it, but I know that there are forms of path tracing that are much faster and less realistic than ray tracing, but I would have to go back and look that up to be able to answer that question really well. But I think, yeah, they were using limited path tracing techniques before they started using full ray tracing. So I think that's the subtle difference between the two techniques. Okay, so we talked about ray tracing, talked about the physics of real light. And so now I'm going to introduce you to something else. It's called Phong lighting, or Phong shading as well, it's called. And it's a completely different idea. Phong lighting is born in an era of, I don't know, I want to say 3DFX, if you've heard of it, or Glide, if you've heard of it. These are the graphics card and software manufacturers of the 1990s era, where this lighting started to appear for the first time. So what happens if we have polygon rendering and we want to do lighting, but we don't have a physics model, right? Because we just don't have... Oh, Voodoo, yes. Yeah, right? So this is Matrox. Sorry, these are all just brand names from the mid-90s. There used to be way more graphics card manufacturers. When it was experimental, when people were trying to figure out what was happening, a whole lot of companies got into it. There was this little one called Nvidia that got involved as well. I think they bought 3DFX, or they were born from the ashes of 3DFX. I think it's something like that. I can't remember exactly. But anyway, before it became kind of distilled into like there was only two companies with the clout to build that kind of hardware, Nvidia and AMD nowadays. Like before then, everyone was trying, so it's like really interesting. So yeah, Simon's like 3D acceleration cards and stuff. That's right, Nvidia bought 3DFX. Yeah, it was something like that. So if we don't have a physics model, so we're giving up on the idea of tracing rays of light around our scene, because we think that it's, even if we can do it, it's so computationally expensive that it's going to cost us so much that maybe we shouldn't. Can we find another way of doing this? Can we find a way of approximating the light? Can we find a way of calculating the light that doesn't necessarily have all these things bouncing around our scene that aren't even going to be used? Can we calculate just the things that we need and stuff, right? So we get to this other part of graphics. I'm going to talk about this later, actually, is that, yes, realism is one thing, but getting it running is another. So can we trick people into believing something while using significantly less computing power? And that's the key, right? It all goes back to the same idea. Human eyes are the only judge of graphics. And human eyes can be tricked because humans are fallible. We're not machines. We're the meat flesh is weak. so we can trick us, right? And we're happy to do that, right? We're happy to believe things if we can be tricked. I mean, as it is, our monitors are only sending us red, green, and blue. There's no yellow coming off our monitors. There's no white coming off my monitor here where I'm seeing white. There's no orange where I'm seeing orange. You know, there's no teal at the bottom here. Like, none of that exists. All I'm seeing is red, green, and blue, and I'm tricking myself into believing it. You know, well, it's not really a trick. It's physiological. It's way below the level of a trick, right? So if that exists, if there is that possibility to trick both our physical light receptors and our processors into believing things, then there must be a way of doing this in the same way for simulating light. So let's look at what we've got available. We've got vertices, we've got triangles, coordinates, we've got our camera and stuff. We've got all our vector and matrix math that we know. And we know that our graphics cards can deal with that thing, although this is a chicken and egg situation. The reason our graphics cards are so good at this maths is because we used this maths to render graphics. It's probably more the other way around. Because people came up with these lighting algorithms that worked in this way, that's why our graphics cards ended up being these massively parallel matrix math processors. You know, because basically all of our graphics cards are hyper optimized to bulk multiplications of floating point numbers. Like that's what it does, and that's what all of these all of this kind of algorithm tech require. So can we build an approximate lighting model that computes a lot faster than the ray tracing model? And the answer is, of course, yes. Because if the answer was no, I wouldn't be putting this in the lecture. So this is Phong lighting. So this is a simple idea for doing lighting in a polygon rendering environment. So this is building on what we have. If we weren't doing polygons and we're doing something else, then this lighting system probably wouldn't work. I mean, it could work, but wouldn't exactly work the same way. So we're talking about like voxel systems, which are different. They're going to use slightly different techniques. We're not going to go into that, by the way. Like, there's too much with just focusing on polygon rendering in this course. Like, I can't really get into voxels, but voxels are cool if you want to look them up. Okay, so let's try to compute light per fragment instead of trying to compute light per light source. I mean, we're still going to be very much tied to light sources, and like the number of light sources we have is going to slow us down, definitely. But if we spin the idea around, you know how I was saying the light emits rays and they bounce off lots of things. Let's go from the other direction. Let's go from the fragments themselves. So we're going to look into our scene, we're going to see things, and we're going to calculate light for what we can see. So what we do is we figure out what we can see first. We've already got that, right? We've done all this maths already. We've done our vertex shaders, our fragment shaders. We've talked about our model view, projection, transforms, all of that kind of stuff boils us down to the idea that for every pixel on the screen, we can look into our scene and say what things that we can see. We are going to see multiple things, especially if there are things in front of each other or there's transparency and stuff, but still, we're kind of at the per pixel level. So we're going to say for each pixel on the screen, we need to calculate lighting. So that's a better idea. I mean, even if we do flip that around for ray tracing, it doesn't work. Because like if you ray trace from a single pixel in the screen, the second you hit something, you've got to expand that into multiple directions and say, okay, let's look in all directions and find out all the light that could possibly hit this point. And then you're at the same blowout of complexity of the number of things. So even if we spun this around for ray tracing, it wouldn't help. But we can spin this around in this system, and it's going to reduce the amount of work that we have to do. We're going to really simplify the idea of the bouncing light, and what we're going to do is we're going to separate this into three different lighting types. So there's ambient light, diffuse light, and specular light. So the Phong system's really about separating this thing into parts, processing them separately, and having each one a simulation of a particular form of the idea of bouncing light and the physics simulation of the bouncing light. So I'm going to go into each of these three in detail. So the first one is ambient light. Ambient light is the thing that we consider to be the the light that bounced off objects in a very indirect manner. So we're talking about light that's had 6 bounces already. So for me here, the light has hit the upper atmosphere, turned blue, come in my window. And so it's come in my window as like a random assortment of light from many different directions. Some of it's bounced off my monitor here, some of it's bounced off my computer, some of it's bounced off the ceiling and the walls and stuff like that. You can tell because they're lit, so some light is definitely hitting them. All of that's bounced around and eventually has hit me. So if I hold my hand up like that, you'll see that's the lights coming out of the window. If I hold it up like this, you can see here there's light, but it's not the direct light from outside. It's bounced off the walls and other things. It's probably even bouncing off my face onto my hand, right? So all of those little reflections, this actually costs a lot, because the more times things bounce, the more calculation is needed to figure out what this is. But the hilarious thing about it is, the more times you bounce off things, the more calculation is necessary, the less effect it has. Because the more times it bounces, the less light it is. So it's really, really funny. Phong lighting is like, don't care. We understand that there's a whole lot of light bouncing around in the scene. We don't care. We just make it constant. So it's so simple. It's like, this room here has a significant amount of ambient light in it, based on the fact that there's heaps of light coming in this window and it's just sort of bouncing around. So what we're going to get is just blanket light the whole room the same amount. And that's going to be kind of how bright stuff is in the shadows. So it hasn't had any direct light, but it's still going to get some light. And so that's it. Phong lighting is so simple for this. We're just like, too hard, not going to simulate. Was it THNS? Too hard, not simulate. It's like TLDR, but like ambient light is the same thing. It's like, don't care. So all it does is says, I'm going to apply a constant amount of light to every object in the scene. So all the stuff we've been working for in the course so far has had this constant amount of light through the scene, but it's been full light. It's been like a 1.0. But in general, our ambient light will be a lot lower than that. So we've had just like the whole scene is always lit. But in this room, like, you know, everything in the shadows would be a little bit lit, but not super lit. So that's what our ambient light's going to be. And then we've got diffuse light. So diffuse light has a direction. Diffuse light has come from a light source somewhere, whether that is like I've got the sun drawn here, or it's a light in the scene, like this lamp. I mean, you can see it is reflecting off my face and stuff like that. So this light has come directly from a source and has hit a surface, and then is simulating the idea that when you hit the surface, it just scatters everywhere. So what this means is that these surfaces are not like shiny. They're not like hard plastic. They're not glass or anything like that. This is everything else. So we're talking cloth. We're talking skin mostly. Sweatier you get, the more shiny you are. We're talking wood. Talking my little miniatures. Someone was asking me to show these on stream. So this is some of the stuff that I painted last week. I painted these little planes, kind of planes. This is like a troop carrier, an airborne troop carrier, and this is like a fighter planes from Warhammer that I was painting. Yeah, so those things, you know, they don't have shiny parts of them. So basically, if the light hits them, it just goes off in every direction. So what we're going to do in Phong lighting for this is we're going to do some pretty simple calculations using some vectors. And we're going to just say that those things that are aimed directly at the light source, and that's a weird concept, so I'm going to go into that in more detail. When I say something's aimed at a light source, actually you can kind of tell. So my hand is aimed at the light source, but as I turn it away, it's aimed less directly towards this lamp. So it gets super, super bright when it's aimed at the lamp, and it gets less bright as it's turned away. So I'm across the lamp, and I've kind of got like these shadows and stuff, but really the light is affecting my hand less because I'm aiming away from it. So we're going to take this really, really simple concept and say these faces of this cube, whatever, they're aimed towards the light in a way, so they're brighter. this face of the cube is aimed away from the light, so it's not going to get any light from here. So it's a really, really simple algorithm that's just going to look at nearly like a triangles as a whole, but we're going to be working with fragments, not just full triangles. But we're going to be looking at which way each surface is facing, and it's going to get more light if it's facing towards the light source and less light as it's facing away from the light source. So it seems logical, right? Understandable. But we can already see how this is a very, very simple calculation to make. We're not having to do multiple bounces or anything like that. We're not having to count the number of photons that hit. All we're doing is looking at an angle towards the light and then changing the intensity of things. So that's what the diffuse lighting is going to be. Specular lighting is the third component. So as I said, with the diffuse light, I said that these are surfaces that are not like hard plastic or glass or anything like that. And they're not reflective surfaces. So we do need to actually do something for reflective surfaces. And this is specular light. Specular light means shininess in a sense. So when we have light from the source that hits an object and it bounces directly off that object into the camera, if that object is considered a shiny surface, so if it is a material that is shiny, I'm using keywords here, material's a keyword. So if we've decided that an object has shininess, then the light is going to bounce off the object. We should, if we're seeing that, we should actually see a reflection of the light source. So what we're doing with specular light is we're going to calculate the direction of the reflected light, and we're going to see whether we're getting direct reflected light into the camera or not. If we're getting direct reflected light into the camera, it's going to change the color that we see on the surface, right? So we're going to see a bright reflection in the surface. We're kind of going to see the light source itself. So this calculation is doing similar stuff to the diffuse light, which is just saying, what are these angles? So all we're doing here is we're saying, if we can see a spot on this object, we can calculate the angle of the angle to the light source, and we can calculate how much the reflected angle of that vector is going to be when it bounces off this surface. And then we're going to say, did that bounce directly into the camera or not? Or how close was it to bouncing directly into the camera? That's how much we would see the bright spot or not. Would we see the reflected bit of light or not? So that's specular lighting. We're not going to get to specular lighting today, definitely. Not even sure how far we're going to get into diffuse lighting today, because there's a lot of stuff I need to talk about to build up our mathematical capability to be able to use this. But these three portions together are going to make up Phong lighting. So here's some scary maths. I just copy pasted this from Wikipedia. Don't be too scared. I'm going to go through with this in detail and break it up into its parts. But this is the basic Phong lighting equation. There are more advanced versions of the Phong lighting equation, which we will go through probably Wednesday, actually. I think that we're going to have time, hopefully, to get through to that on Wednesday. So here we have the ambient component. So I said ambient was pretty easy. Light color, the amount of ambient light in the scene. So for my scene here, I've got a whole lot of ambient light just kind of bouncing around. It's mostly like a yellowish kind of color, I think. The color from the sun is a little bit more yellow than it is white. But anyway, but it's bounced off green from trees, blue from atmosphere, and all this kind of stuff. So who knows what color it is. But what it is a dim amount of light that's in the scene. I think the I is actually the light, and the K here represents the surface color. So ambient light everywhere. Oh, Simon's saying sunlight is pure white. I didn't know that. I mean, it's definitely gonna have something to do with the just the spectrographic properties of it. Actually, it makes perfect sense that sunlight is pure white, because pure white is a human construct, right? It's a selection of spectrums and a balance of all those spectrums, and obviously we would see, like, our vision evolved using the sun as the reference. So our entire capability to see things is based on the light from the sun. And you'll see this very interesting because animals that can see in the dark can see into infrared. So their version of what they would see as white involves infrared as well as red. Whereas for us, because we're daytime animals, well, mostly daytime. I know you're all gamers, and you don't wake up in the mornings, because I don't either. But anyway, yeah. So so that's why we consider that white. You know, all colors are a human construct. Otherwise, they're just wavelengths of electromagnetic radiation. Anyway, getting back into it here, right? So I've got a certain amount of ambient light in my scene, and so this is illumination at a point, because this is a mathematical equation. They're not looking at fragments here. They're not looking at pixels or anything like that. That's us. When we do the engineering side of things, we go into those details, right? So illumination at a point is made up of the ambient plus, for every light in the scene. So there's multiple lights in the scene, then each light might affect our particular fragment. This bit here is the diffuse. So it has the same thing with a K and an I. So the I is the intensity of that particular light. So M is in lights. So I don't know how much maths everyone's done, but I think this maths is not super complicated if I explain it. And anyway, I'm going to spend a few hours explaining this. So if I'm going to spend a few hours explaining this one algorithm, you'll probably get it by the end, right? And then we've got these two vectors here. They're going to get dot producted. I'll talk about that later, but the K and the I are there. So most of the time you're multiplying the amount of color that's in the light. So color, intensity, I'm going to use lots of different words for the same kind of thing. It's just an RGB value. So the higher the numbers are in the RGB value, the brighter that light is, or the more reflective, more colorful that surface is. I mean, you can't really say colorful, because white is the highest numbers, and that's not colorful at all. So many different ways of talking about this. We can talk about this from an art perspective, and we can talk about this from a technical perspective. So when I'm saying colorful, I mean it has lots of color. If you combine lots of color, you get no color. Anyway, but yeah, so we have the color of the surface multiplied by the color of the light, multiplied by some other mathematical factor. I'm not going to go into more detail than that. I will go into more detail later. The specular light is the same thing. The specularity of the object multiplied by the specular intensity. So this is why this is an I, the intensity of the light. So there's the light here, the object here, and then multiplied by some other factor. And these other factors here, these things with dot products in them and vectors and dot products, are the things we were talking about angles. Right, so this is the angle of the light to the object. This is the angle of the light to the eye after it's reflected. But I'm going to go through all this stuff in detail later on today, as well as on Wednesday. We're going to go into this stuff and have a look at how this actually works. But if we add all three of these things together, then we get the total amount of color in the fragment. So I've got some kind of explanation here, but we're going to go into that in much more detail later. So let's take a break. But I did want to, and I said I was going to talk about this. I did want to talk about this because it's quite interesting. I think I've said this before, but it bears repeating. The entire field of graphics is dirty hacks on optimization. I say dirty hacks, they're not dirty in the, like, you know, when you code something for like an assignment and then the thing's due in like 3 hours, you start coding dirty. It's not that kind of dirty, but it is still, like, for example, this one. Correct calculations take a lot of light bounces. They don't usually have that much effect. How about we don't do any of that? That's it. That was our solution to not being able to do a great number of ambient reflected rays. You just ignore them. Screw it. The entire scene has 0.1, 0.1, 0.1 in its RGB. That's it. 1/10 of the possible scale of light is just spread out over the entire scene. And that's it. Like, so little thought went into that, but probably a great deal of thought and experimentation went into that to get us to the point where it's like, you know what, this stuff doesn't matter. People can't see it. They cannot tell the difference. We just let it go. Many years later, people would come up with the idea of ambient occlusion and fix some of the problems that came up from this assumption. But we're going to use this assumption anyway. What is the trick there? The trick is that putting a blanket of a small amount of light across the entire scene made us believe to a certain extent that there was like sort of just some light floating around and we didn't have to calculate any of it. So it's super, super cheap. Super cheap, super fast, and doesn't take us into the realm of having to do something like ray tracing for ambient stuff. Yeah. Cineo saying, high graphics settings doesn't change much compared to medium, but eats up a lot of performance. Yeah, totally. Totally like that. Okay, so polygon rendering itself is a big trick to reduce the amount of computation. So what we do in polygon rendering is we've abandoned the idea of any curved surfaces, which is deeply ironic because nature has no flat surfaces, right? So because all we had was maths, it was like we can just approximate an entire big surface of things by putting some verts around it and just doing flat surfaces between them. It's much easier to calculate. We can tell exactly where things are if they're triangles, and so much work has been done in graphics since to get things that are made of triangles to look like they're not made of triangles. So it's really interesting. So you see this much more in games than you see in films, but it's still definitely there in films. It's always, how fast can we render this versus how good does it look? And how good does it look is just such a nebulous idea. You know, does it look better than a previous thing? And what does better mean? Does better mean more realistic, or does better mean we found a way to make a cool effect that people are excited about? You know, so there's a whole bunch of stuff there. But one of the things is that light is a semi-conscious assumption for humans. So if I see something that's casting a shadow, I see something that is reflecting light, I assume that that is correct, you know, in the world around me. So it's easier to throw people off by doing your lighting wrong than it is to do other things wrong. So your physics of, I don't know, some kind of like superhero plumber jumping at bricks and breaking them with his head. I mean, it's kind of his hand as well, right? We just let that go. You know, it's like, yeah, whatever. He's a superhero plumber. He can just break stuff. It's like, okay. So we don't even care a lot of the time about whether physics is correct or not. But light is less conscious. And so we will believe that when it works, and when it doesn't work, we notice. You know, there's heaps of games don't have any lighting at all because they're just like, yeah, let's just not do it. You know, like all your 2D games and stuff like that, they'll have a very artistic look at light instead. But when you get to your kind of third person, first person shooters, that kind of stuff, you get to those really, really specific kind of games that want you to believe the world you're in. They want you to be immersed in the world you're in. They can have a whole lot of lack of realism. But if the light isn't realistic, then we're out, you know. So there's this kind of thing where, can you get that visual quality within the amount of time so that your animations are still believable? Because your animations, your movement are only believable above 24 frames a second, and they're only comfortable above 60 frames a second. And if you don't have that, it doesn't matter how good your visual quality is. You've just got a very pretty slideshow going there. Well done. But if those images don't meld into each other, so we're in this constant struggle back and forth between the two. All right, let's go on break now. It is 5:08 now, and we'll come back at 5:13, and we'll start delving into said algorithm, and we're going to pull it apart, show you how the bits work. I will probably start building up an actual example. I'll start drawing some pictures and like looking at some numbers and things like that, and showing you how these things work. All right, back soon. All right, we're back. All right, as I said, I think. Actually, I know I haven't yet, but I think I've given you enough groundwork to start talking about the algorithm. I haven't. There's a few fundamental bits and pieces that we need to talk about, but I'm going to talk about that as we go. So I'm going to go through now ambient, diffuse, specular. Specular we're not covering today, no chance. But when we get to each of these things, I'm going to add some pieces to your knowledge that are necessary to be able to use these things. So ambient's going to be pretty easy, but when we get to diffuse, we need to kind of backtrack a little, talk about some things that we kind of know. We don't have to know them all, you know, but I'm gonna build up your knowledge and go back over some of the things that we've learned previously, because, like, you know, we can't really do lighting without a good understanding of how our objects actually exist. So we're going to talk about the way that we use triangles and stuff like that to get there. So, oh yeah, we're not even at that point yet. I love my own slides. Like, it was really funny when I was making these slides. I was like, okay, I want to teach this and teach this. And so if I need to teach this, I need to go back and talk about these things. So let's talk about lights and materials, right? Okay, so where does light come from? In the real world, it either comes from the sun or our artificial lights. That's it. We've got things that generate photons. There's plenty of other things that generate photons, like a computer monitor. Like, most of the light on my face is from my monitor, I think. Like, some of it's from the window, but most of it's from the monitor. I can tell because it's very pale. It makes me look very washed out. And that's always what I look like. Everyone thinks that I'm super pale because, like, you've only seen me in lectures, but, like, I think if you see me in real life, it's like, oh, he actually looks like a human. Anyway, real world's the sun, or like the sun, as we consider, is something off in the distance. Lamps and light bulbs are things that are actually here with us. So in our virtual scenes, we're going to start with two types of lights, which is going to be a directional light, and a directional light comes from a certain place, but it doesn't, we don't even think about it as coming from a certain place. What we think about is all light from the sun is coming one direction into our scene. So it's like, if the sun's up there, the light comes down, and then no matter where it hits in the scene, it has the same direction that it comes from. It actually makes it easy for us to do things, because we don't have to calculate the direction by saying fragment to emitter object, calculate, like, minus the two vectors to figure out what direction it's coming from. We just go, this is the direction of the light, which is why we call those directional lights. And then we also have point lights. Point lights are a position in the scene. So a point light is interesting because it doesn't actually have any volume. So it's kind of impossible in the real world, because everything that emits light is a physical object that emits it from an area on its surface. Like, the computer monitor is a huge example. It's like a massive surface that emits light. But this light bulb, you could think of it as a very small object that emits light. And so in our scenes, we're going to think about... I just shone that straight into my eyes. Too many photons! In our scenes, we're going to think of things like lamps and stuff like that as being a single point in space. So we're just going to represent these by a vector. And it's going to be just a vector that is a position in the same way that a vert somewhere in our scene has its position, or the center of an object and stuff, right? So it's just... we know how to do this. It's a coordinate in space. And then we're going to use that to decide how much light it gives to other things. It's something that's not even going to be rendered, you know, unless we make a lamp model or something to attach the light to. It itself is not necessarily going to be rendered. Its effect on other things is what's going to be rendered. There are other lights. So there's things like spotlights, we call them. So actually, this is a decent example of one. So it's shining most of its light in a specific direction. That's just a point light with some restrictions put on it. And we can do lots of little things like that with lights. When we get really advanced, we have lights have a limited amount of range as well. So that's kind of cool. Oh, oops. I just spoke about this. Yeah. So the directional light is a vector. It's a direction, and it always comes from the same direction. And the point lights is a position. So if we need to know the direction from a point light to a fragment, we have to calculate it. Not hard to calculate though, because we're just minusing one point from another. We get the direction between the two. Materials. So I said this word a few times. I was waving it around in front of you to get you to familiar with the idea of a material. So a material is what we think of as something that is part of the surface properties of an object. We have been using textures. We've been calling these things textures, and that has given us some material information for our objects. The texture is a color, is color information of the surface. And that's very important, right? That's why we teach it to you first. Excuse me. So we taught you about textures, which is, for example, this t-shirt. If we were going to do geometry for this t-shirt, we would not put all these extra vertices in here for the print on the t-shirt. What we would do is we just go, all right, model it as a generic t-shirt, plaster this particular texture on it. The texture will have that image information. So that's a lot of the color information. That's going to be important for lighting. But that's not the only thing that's important for lighting. We can use other materials for our surface. So we could have a material for our surface saying some parts of this thing are shiny and other parts are not. Do I have a good example? Kind of. This plastic container, this is my chocolate supply. Here, I love it's right next to my desk. Parts of this container, the handles here are not shiny at all. Other parts of this container, this plastic surface, flat plastic surface here, are a bit shiny. So we can actually have a material, also called a map, also called like a texture as well, on the surface of this object, which tells us which bits are shiny and which are not. In the same way that we had textures telling us which parts are particular colors, this would totally have a texture where parts of it are blue and parts of it are some kind of white. Awkward because of the transparency, what you'd have for the colors for what's inside, but you know, we're not talking about that too much right now. But yeah, we can have other things, so we can map more than one thing to the texture coordinates on an object. So we can map multiple different two-dimensional surface information materials to one object. And so yeah, we can have like, how shiny is that object in different places? Does the object itself have things like bumps and ripples in its surface that are not modeled in the geometry? Maybe we were going easy on the geometry and using a bunch of flat surfaces to reduce our poly count and stuff like that, but we still want this thing to have a particular kind of roughness to its surface, and so we could put materials on it to do that kind of thing as well. So multiple different materials for an object. You can see in this we have how much light the object reflects if it's ambient light, how much light the object reflects if it's diffuse light, how much light the object reflects if it's specular light. Now, the ambient and diffuse light are often going to be the same value because this is just the raw color of an object. But if I have something that is, take for example, no, I want this off. My phone that is off. So the interesting thing about my phone is on ambient and diffuse, it reflects nearly nothing because it's black on ambient and diffuse. Yet on specular, it's like a full white. It's like, there you go, there's the reflection out the window. It's reflecting all of that light. So you can actually have different textures on an object for different kinds of light. So if we're talking about reflective light, that thing's super reflective. But when we're talking about ambient and diffuse light, it's black. So it's reflecting very little light. So you get this kind of thing where you may want different textures for the same object just for different types of reflectivity. So yeah, where are we? Yeah, so these are the materials that we can use, and we're going to be sampling these materials every time we do lighting, right? As I said there, you know, I can have a specular texture on an object. We often call them specular maps. And I can have a diffuse map. I mean, that is technically what a texture is. Like, we call them textures as like a colloquial term. Technical term for a texture is a diffuse color map. So that's kind of, now that you know that there's multiple things, you know that the texture is probably the diffuse color of the object. And then we can have things, you may have heard of things like bump maps and normal maps and things. We're going to go into that a little bit later. Okay, So let's get started on the algorithm and pulling it apart and seeing how it works. Ambient lighting is going to be quick because ambient lighting is pretty easy. So this is calculated per scene per fragment. So we would pick a fragment. So this is the way that we would be doing things. Normally in our fragment shader, we would be viewing the scene and calculating the color of a fragment. And if we're going to calculate the color of a fragment accurately, we don't just want the color of the fragment, we want the color of the fragment as influenced by the lighting in the scene, and then we'll see what it looks like. So the ambient lighting is really simple. Two numbers multiplied together to get another number. So the number that we're looking for is the final intensity of the ambient light at that fragment. So remember, a fragment is part of an object in a scene that is viewable kind of through 1 pixel. So we're looking at 1 pixel, 1 object in the scene. It's not necessarily that definitely what that pixel is going to be, because if there's multiple objects that can be seen through that pixel, it's going to be the closest one that is the one that's finally rendered. But we're going to check all of them because we don't know which one's the closest until we've played around with the Z buffer. Having said that, we probably don't do lighting for things if we can see that it is not visible. Anyway, so final intensity is equal to the intensity of the ambient light in the scene multiplied by the ambient reflectivity of that fragment. So when I'm saying ambient reflectivity, that is going to be whatever is in the ambient or the basic color texture for that fragment, for that object at that fragment. I wonder if I should start drawing some pictures. Oh, Hamish has just picked out an issue here. I got my blues and my greens mixed up. Anyway, we'll talk about that in a second. So, an example here. Let me fix that. 0.2 and then 0.9, which means that's 0.2. I should have just changed the word blue to green. That would have been way easier than what I'm doing. Anyway, I think I fixed it. Have I fixed it? Yeah, there you go. All right. So, this is the simple one. It's just multiplying numbers. So, what we're going to get is the color of the object and the amount of ambient light in the scene. It's going to be dark because we don't want our ambient light to be lighting the whole scene. Because if our ambient light is lighting the whole scene, then there's no interest in our light. We really want the diffuse light to be the majority of the light in the scene, so then we can see the direction the light's coming from and stuff like that. So, for example here, let's say our ambient light is a bit reddish, but as you can see, the numbers are quite low. So it's got a little bit more red than it has blue and green. So it's a warm light. This could be reflected light from, say, a campfire, or if you're going to be more sinister, it's a room that has, like, you know, a bunch of, like, red warning lights in it, and this is just the ambient light from those. So it's reddish. And then we have an object that is mostly blue. So this thing, that blue, and like, so it's just reflecting mostly blue light, right? So the only thing that we would get for rendering a fragment that is on this blue object in a reddish scene is we just multiply these numbers out. So multiplying these two vectors, it's just, you take 0.1 times 0.2, we get 0.02, 0.01, and 0.45. 0.045 or 0.45? Oh no, 0. Yeah. So there's so little light on this object. So you can see it's very dark. It's a little bit more blue and a little bit more red than it is green, but that's it. So Bob's asking, is this all done in the shader? Yes, this is all done in the shader, because as I was saying, if we're going to do this per fragment, this is happening in the fragment shader. So the fragment shader is going to, at this point, it's going to pick up object information, and we do this normally, right? We've been doing this before with our fragment shader to get our frag color. In fact, our frag color is this KA. At the moment, if you took your scenes and just wrote the same code that you had in the frag shader, and this KA was actually just the color of the texture that you were sampling for that object, and then you started multiplying it by ambient light, what you could do is just dim down all the light in the scene to say there is this much ambient light. And this is going to give you an even amount of color across the entire scene. So we've got an example here. It's not much yet. But we have a light source which is really close to the camera, so that's actually, they're not two cubes next to each other. I'm pretty sure that in this rendering it's pretty far away. This is from Learn OpenGL. They do actually have some code that you can play around with, and you can move this around. There is a cube here, and there's a black background. The cube barely has any light. It is visible against the black background, but just like in my example, the ambient light's quite low. So we're going to assume that once the light has bounced around enough times to be ambient, to be thought of as kind of being everywhere, it's lost a lot of its intensity to do that. So direct light more important than ambient light, but it's here. And also you can see that we can't even see the front corner of this cube or anything like that, because everything in the cube is lit evenly. So if it's all lit evenly, it's the same amount of light across the whole thing. There's no textures on it either here, so you can't really see anything. So yeah, that's the basics. Ambient light. Fragment shader picks up the texture or just the color of the object, multiplies it by the ambient light in the scene. So that's the easy one. So getting into the harder stuff, I can't talk to you about diffuse lighting yet, because I must talk to you about these things called normals. And this isn't just people who don't know about computer games. I kid. That was mean. But it's kind of funny that I don't consider myself a normal person. Okay. Hello, fellow humans. I too also am a human, not just a robo lecturer. Okay, so normals. Not talking about people anymore. That was just a minefield. I was going to say something very bad if I kept going in that direction. So, diffuse lighting does need to know where a surface is facing. And the way that we represent where a surface is facing is by using a vector. So we use a vector that is kind of attached to the surface in a way, and it says this surface is facing in this direction. So if we have a cube like this, it's pretty obvious where we expect the faces of this cube to be aiming. We expect these things to be aiming directly off the faces. So the definition of a normal, the mathematical definition of a normal, is something that's perpendicular to the tangent to a surface. So even on a curve, you can get a normal, because at any point in a curve, there's a tangent, which is a straight line, and then the normal is perpendicular. 3 dimensions, you can be perpendicular to a plane as well. That makes perfect sense. And that shows you which direction this particular polygon is facing, triangle or square or rectangle. But most of the time we're going to be working with triangles. So, can we attach normals to triangles? The simple answer to can we attach normals to triangles is no. Because a triangle has no data, right? There's no struct that is a triangle that we're using. So the only place that we can store information is in our vertices. And so there's a couple of different ways that we can do this, because already you can see a problem here, right? What's the normal at this vert? And it's like, well, that's awkward. Is the normal at this vert this one? Or is it this one? Or is it this one? So there's some issues here. So sometimes we're going to be storing normals in our vertices, but sometimes otherwise. Sorry, I'm jumping ahead of myself. Yeah, I'll talk about that in a second. My slides just reminded me there was something else I wanted to say before we got there. Normals, we can store the normal data in the vertices, and that's good because our fragment shader is used to grabbing information from vertices. So our fragment shader is already going to grab information from multiple vertices around itself, usually the 3 vertices around itself, and linearly interpolate between those 3 to get one piece of information. So your texture coordinate is linearly interpolated between the three texture coordinates in the verts around it. You can do the same thing for normals. So we can put a normal on each vert on a triangle, and then we can linearly interpolate between them. I mean, for something like this cube, that's really easy, because if we had, for this one, if we had the same normal on all 4 corners facing upwards, and all we did was have the same normal anywhere on this surface, that would actually be correct, because it's a flat surface facing in a particular direction. So the issue there, though, is if we have these verts that are getting used in multiple faces, maybe we don't want to store the verts there. We can generate the normals instead. So there's two different ways that we can do this, and we're going to use this for different kinds of objects. So one way is we can generate the normals just using the triangle data. But the other way is we can have a specific normal that's stored in the vertex attributes and will linearly interpolate between them. Either way, what we're going to end up with is anywhere on that surface. We hit a fragment anywhere on that surface, we're going to have a normal that's going to tell us exactly which way that surface is facing. So let's talk about generating normals, because this is another interesting thing. If we have triangles and we don't have any normals, we can still make normals, because we can just take a cross product of two sides of this triangle. Is it right hand rule? 1, 2, 3. Yeah, I think it's right hand rule. Wait, no, it's left hand rule. Oh, I forget. I remember reading somewhere that Unity did a cross product with a left hand rule or right hand rule instead of a left hand rule, but anyway. I will remember this as I start talking about it. So if we take a cross product of the triangle edges, now recall what the cross product does in visualization of vectors. A cross product says that if we take any two vectors, we will create a third vector which is perpendicular to both of the other two. So any two vectors made out of these three verts are going to be on the plane that that triangle exists on. If they're on the plane that that triangle exists on, then a cross product of any two of those is going to be the normal to that plane, either coming up or down from that. And that's where it becomes important, because we do actually need to be able to tell now which way every triangle is facing, because if it's going clockwise and we're picking things picking, say, these two normals, 1 to 2, then 2 to 3, that'll give us a certain normal. It'll either be going in or out of the triangle. If we go counterclockwise and we go, say, 2 to 1 and then 1 to 3, then we're going to get a normal facing the other direction. And we have to make sure now that each of our triangles has a front and a back. Now, I mentioned this like a month ago now, I think, that when we started building triangles, that the order in them might actually have an effect later. And now we're seeing that effect is that there is a front and a back to every triangle. And this depends on the winding order, it's called, which is like which direction we specify the verts to be used for the triangles. And so the convention that is used I don't think it's just OpenGL, I think it's all polygon rendering. The convention is that counterclockwise winding of the verts will show you the front of the polygon. So if I'm looking at the verts and the order I've been given to them goes, say, 1, 3, 2 here, so it's a counterclockwise ordering, then I'm looking at the front of the triangle. If I can see that the winding is 1, 2, 3 here, this triangle, I'm looking at the back of that triangle. And the interesting thing about that is this is actually how OpenGL decides which triangles are visible and which aren't. So I don't know if anyone's tried this yet with your cameras that you've been playing around with and cubes and stuff like that. You can move your camera inside the cube. When you move your camera inside the cube, the entire cube disappears. And it does that because the winding order on those triangles was making you look at the back faces of the triangles, not the front faces, but only the front faces will render. The back faces will never render. Again, this is a trick that helps us reduce the amount of computation complexity of rendering things, because if anything's facing away from you, you just don't see it at all, and your render knows not to have to render it. So yeah, Simon's saying assuming we have backface culling on. I just assumed that was on by default, right? I don't know if it's not. So with this winding, yeah, okay, good. Simon's like, assuming you have backface culling on, which we do, yes. So, we can then generate normals from these triangles, and the best thing about this is if we remember this counterclockwise thing, we know that our cross product is always going to give us, if we're looking at a triangle and the verts are going counterclockwise. Wait, from your view, I'm gonna make sure I'm doing it from my view, and then I have to do it that way. From your view, counterclockwise. If you see counterclockwise, then the normal's pointing towards you. If you see clockwise, then the normal's pointing towards me. So this way, what we can do is we can actually say, look, we don't really care about what's in the verts. We only care about where the verts are, and we'll make our own normals. So you can just make any kind of object, and we can say, look, we know exactly where the surface normal is, because all we're going to do is take the verts of the triangles, do a cross product, and then we have our normals. And that's what we get in this situation, where if we want these to be perfectly flat surfaces, we can just generate the normals based on the triangles, and then we're going to get these normals that just come out of these surfaces. Now I say these because this is important, because without the normals, we don't know where the faces on our object are actually aiming. And I should point out this. This is something that's going to come up a fair bit. You are going to find out if you're playing around with code, you're going to find out that sometimes your lighting equations go a little bit strange. And that is because anytime that we have a direction, so I've been quite careful in a lot of the slides here to talk about certain vectors as directions, because a vector has two kind of data components. You can think of it as a direction as well as a magnitude. So a vector is kind of like saying, I'm an arrow pointing in a certain direction. If you move the base of the arrow to 0, then you can say that is the coordinates of the vector. And so it's going to be pointing in some direction, so in our three-dimensional space, some direction, and it's going to be going a certain distance in that direction. When we're using a vector purely as a direction, it's quite important that we make sure that it doesn't have a magnitude that's going to affect things. So the default magnitude that we want from a normal, so the normal, normalizing normals to make them normal, the normal length of a vector is 1. And you get this by normalizing. There's no nice way to say this because it's just all the same word. When we're doing our lighting calculations, anytime we're using a direction vector, we're expecting it to be length 1. Your lighting will not work properly if your directional vectors, like your normals, which are just the directions the surface is aiming, are not length 1. The calculations will not work. So for example, like, actually, no. We'll go into the maths later. I was going to show you the maths and why it won't work, but I need to explain that maths first. So yeah, when in doubt, normalize vectors. I mean, directional vectors. If you normalize something else that's actually the position of an object, then you're going to have a problem, right? It's going to move that thing to one away from the origin of your coordinate system. But anytime we're using directions and things, so the normals to the surface, we're always going to normalize them so they end up length 1. There's also a lot of situations where you get caught out by this. So you may have normals put into your vertices and things like that, and then you don't realize that they get caught up in transforms. So you've scaled your object and then the normals get scaled. So what we're often going to do is we're just going to normalize things just before we use them. So even if something has been scaled, its normals have been moved around, and things like that, we're still going to normalize them. So for example, if we cross product any two vectors in a triangle, we're not going to get a 1 length vector. I mean, if we're really lucky, we might get a 1 length vector, but most of the time we're not going to get the perfect 1 length vector. So before we pass this normal into our lighting equation, we're going to normalize it and make it length 1. All right. Yeah, and as Simon's saying there, the interesting thing is that when we're using coordinates, the fourth coordinate, the W, is a 1, but the directional vectors, the fourth component, is 0, because we don't want that. And that's actually the way that you can read them to see that they're different. Is that the if you got a vec4 for your directions, the W will be 0 to say that I am not a homogeneous coordinate, as we call them, is like the positions in space that are going to have transforms applied to them. The directional vectors should not have transforms applied to them, because their direction should be kind of absolute. You translate a direction to somewhere else, it shouldn't change, right? And the 0 stops it from changing. Dongju said, time to use the Quake fast inverse square root formula. I have a video, there's a video about that keeps popping up in my feed. I haven't watched it yet, but maybe I'll share it to you later. Okay, so now with information that we've learnt about materials, light sources, materials, and normals, we're now ready to look at diffuse lighting, because diffuse lighting had directional vectors in it. So without me saying we normalize things, we're not ready to actually use that. So, how much time have we got? Okay, I'm going to start diffuse, but this is going to be a to be continued, I think. I can talk a bit about it, but I think we're going to run out of time before the end of the lecture. I will recap it at the start of the next lecture. So, we're calculating this time per light per fragment. So we're not calculating it once per scene. So the ambient lighting, we usually calculate once per scene, because we consider none of the individual lights to be in control of the ambient lighting, but all of the lights in the scene to kind of be contributing to the ambient lighting. Whereas diffuse lighting, we're talking about a direct reflection from a light to an object to the camera. It's not really a direct reflection, but it's like the light hitting the object determines how bright it is. So if I have multiple lights in my scene, each one is going to contribute in some way to the diffuse lighting of an object. I mean, sometimes if the object is facing away from the light, we'll get no light at all. But anyway, let's get into the maths of this. All right, so this is per light. So every light's going to go through this and then add up to the intensity. So intensity D here is the intensity of the diffuse light. So this wasn't in the original equation. This is just because I'm breaking it apart into 3 parts that are going to get added together. KD, so the K should probably start to recognize this, is the diffuse reflectivity of the fragment. Now, I could have said the diffuse color of the fragment, and you can understand that as well, but I wanted to use the word reflectivity because this is talking about the colors that this will reflect. Because the only light that we're going to get from this thing is the light that's coming off the light that's coming off the light and then reflecting off the surface. Kill death ratio. There's an A later in the algorithm, so I could call this KDA. Anyway, so the diffuse reflectivity of the fragment multiplied by the diffuse intensity of the light source. Now, sometimes this is just the intensity of the light source. Sometimes we don't actually separate how a light source interacts with either diffuse or specular objects. Like, it's up to the object to decide that. So often the intensity of the light source is just the intensity of the light source. So those two multiplied together. Then the important thing is this dot product here. So we need to talk a little bit about dot products. Do I have a slide for this? Yes, I did. Okay, good. So what we have is one vector, which is the direction to the light from the fragment, and n is the surface normal at the fragment. I could have written at the fragment there, but you kind of get that the surface normal is not just the normal at the fragment. It might be the surface normal across the entire triangle. So let's break this down. What is this L dot n? So a dot product of 2 directional vectors. Now, if you recall how a dot product works, a dot product is a way of multiplying 2 vectors. It's not really multiplying, but it's got multiplications in it. But it's an operator that works on 2 vectors and it results in a single number. And that single number is a scaling value of the difference between the directions of the vectors. If the vectors have length, it's more complicated because it is like a projection from one vector onto the other, but I don't think we want to get into too much detail there, because what we're going to assume here is that these vectors are both length 1. And what we're going to get out of this, yeah, Simon's got the actual maths there, is a relationship to the cos of the angle between the two vectors. And the cosine of the angle between the two vectors has some interesting properties. So cosine starts at 1 if it's at 0 degrees. When it gets 90 degrees, it's at 0. The cool thing about this, if the two vectors are aimed directly in the same direction as each other, so this is my surface normal of my object here, is pointing straight up, I create another vector aimed at the light source. So to do that, I'm going to need the coordinates, right? Coordinates of the fragment and the coordinates of the light source. So these are things that need to go into the shader, right? The shader needs to know where the light source is for each light, and the location of the fragment. Location of the fragment is something that we have already been able to pick up before. So we create this vector, and then dot producting those two vectors is going to give us a scalar value. And because it's a cos, it just goes up and down between -1 and 1. The trick is here that if the light is coming 90 degrees to the surface, so that's kind of like I showed before, that once I am 90 degrees to this light source, the light source kind of stops affecting it. And this is hard because this is not a normal light source, and not a simple light source like we get in our graphics environments. But basically, if you're aiming directly at it, you're brightest. If you're aiming across it, you have no effect on it. So this is like 90 degrees, you have no effect on it. 0 degrees, you have effect on it. We are going to ignore any values that we get that are below 0. So we're not going to negate light. We're not going to take light away from something. We're only going to add light if it is aiming towards something. So what we're getting is the light is the brightest when the light shines directly at the surface, and then if there's no if the light is shining across the surface, the light has no effect on the surface, and every kind of possible angle in between is going to have a scalar value. So the cool thing about this is we have color of the object, color of the light, multiply them together, but multiply them by a scaling factor that says that we're only going to get light if we're facing somewhere towards the object, and the amount of light we're going to get on the object is going to be based on how close we are to aiming directly at it. So 45 degree, we're going to get like, what is it, about 60% of the light, 90 degrees, 0, and straight on, we're going to get all of the possible light between that color and the color of the fragment. Did I just say this? Yes. So, intensity of the light and the diffuse reflectivity of the surface, we multiply those just like ambient lighting, and then we factor those between 0 and 1 based on how directly the surface normal aims at the light source. So if the surface normal aims directly at the light source, full light. If it aims like away from the light source, we get no light at all. And the nice thing about that is all we have to do is do a dot product there to get that information. Oh, we do have to find the direction to the light, but that's just going to be minusing 2 vectors and then minusing 2 positions and then normalizing them. And the surface normal, either we're going to generate it via the cross products, or we're going to pick it up from the vertices nearby. So that is going to get us our diffuse lighting. And it's going to look a little bit something like this. So, should say that this light, this cube, is very, very close to us, this little cube of light. And then you can see in the diffuse lighting that this face is aiming towards the light, so it gets more light. And if you can see closely, it's actually brighter in the top corner than it is in the bottom corner because the angles are different in across the different parts of the surface. The top surface is aiming upwards. It's nearly 90 degrees from the light, so we're not getting much light there. This side one is also aiming very much away from the light, so there's less light there, but there's a little bit more light than there is on the top, implying that with this cube and this light, the light's kind of offset to the side and not too much above the source. So already what we're getting from this diffuse light is a representation of how much light an object should receive based on the directions that it's looking at it. Um, I did want to actually do a little bit of maths on this and show it, but I think we're pretty low on time, and I don't want to start it now because we're close enough to the end. So what I'm going to do is we'll do more of a walkthrough on this at the start of the next lecture. So the next lecture is going to be finishing off the diffuse component and then going into the specular component and how it works. So I might actually wrap it up here because I feel like, I mean, 8-minute early mark's not that big a deal. Because I feel like what I've done today is I've just dumped a whole bunch of information on you, and I think it's going to take some time to get a handle on this idea of like, this is the maths behind how we're going to be doing our lighting. It's reasonably simple maths, but there's just so many components and so many moving parts in that. Whereas it's not just this, right? It's this, but then we have to talk about materials, we have to talk about surface normals, we have to talk about different types of lights and stuff. So really today I just wanted to set up this ecosystem that we're going to be doing maths in for a bit. So what I'm going to do next time is we'll step through, like I've stepped through talking about it, but I want to do a more practical example next time. We're going to actually crunch the numbers, punch them into a calculator and stuff like that, and look at how different angles to different lights are going to give us different intensity values and things like that. Okay. So I will wrap it up there and say, okay, what did we learn today? You've got to go back over everything to remember this. So we're looking at what real light is, what the physical properties of light are, and the difference between us being able to just see this stuff and us wanting to simulate this. So we looked at a couple of different possibilities for the simulation of light. One of them is this magical buzzword that sells graphics cards called ray tracing. And how it is actually a good, accurate way to simulate lighting, but it's an expensive simulation. So whether you've got a spare $3,000 for a 3090 graphics card or not, that's going to cost, right? And so instead, what we're looking at is a historical idea of lighting called the Phong lighting or Phong shading algorithm, which is going to get us a pretty good look without costing nearly as much processing power. The Phong lighting model is the basis for most of the lighting that we get in real-time situations in games and stuff nowadays. And I think that you can't do a lot of the other lighting things without this basic understanding of it, because it's a pretty simple thing. So we're just bouncing some stuff around, and then we're getting our lighting based on how things bounce. Oh, Hamish is asking whether Wednesday and this week's tute will have all the required content for the assignment, or we need to do week 8. I think we do need week 8 as well. Oh, Simon's already answered that. Yeah, we're going to need week 8. Yeah, and so I'm saying, depends on what Mark says. We could potentially release the tutorial 8 early if people really want to get a jump in it, but it should be that we will finish teaching everything in week 8, and you'll have a whole week after that to add on anything from week 8 into the assignment. So hopefully that's okay. It does make that week a bit of work, but then I don't know. I think a lot of people, if we give you the content and give you a week afterwards to complete it, and that's only a part of the assignment, should be okay. You can actually do sort of from this week, you can do sort of 2/3, at least 3/4 of the assignment. So hopefully that's enough. Yeah. Okay. The other thing we did was introduce the Phong lighting algorithm and how it approximates light, and we started putting together, we've collected our building blocks for it, but we haven't gone through the whole algorithm yet. So we're going to do more of that on Wednesday. We're going to go through the diffuse and specular components and do the maths on it and some demos of that. And so hopefully by the end of that, you should be able to fully understand how to apply the basic Phong algorithm. I say basic because there's a lot of extensions to the Phong lighting algorithm, but we're not going to look at them just yet. Maybe a bit on Wednesday. I'm going to see how much time that we've got there. Yeah. So that's where we're at now. I'm going to wrap up the official lecture here. and then come back afterwards in a second for any questions if people have any. So I'm going to go to the Be Right Back screen and I'll come back in a sec. I'm back. I didn't think we were going to get through that whole lecture in 2 hours today, which makes me a bit concerned that maybe I've gone through the details too quickly. We'll see how we go. I think what I might do is slow it down on Wednesday, and instead of just talking through the algorithms, I'm going to actually step through and put some numbers in and crunch those numbers. And we'll look at the numbers that come out from, like, I'll put multiple lights looking at a particular fragment, and we can see how they're different levels of brightness based on their different angles to the fragment. I think it's important to see that. Specula is going to take a little bit of time as well because it's got 1 or 2 more moving parts than the others, but shouldn't be too bad. Okay, just checking if there are any questions. Wait, it's saying my audio stream. No, it's fine. There was a warning saying my audio stream wasn't working. Oh, Simon's asking about what happens if we do all the light in the vertex shader. I wasn't going to talk about that. It's too old. There is another form of lighting called garage shading, which is like pre-Phong shading, where what you do is instead of calculating lighting at fragments, you calculate the lights in the vert shader. So you calculate the amount of light at each vertex, and then you just linearly interpolate across all the triangles. We haven't done that for quite some time, but we could look at it, because that is a way that you can do lighting that is way, way more efficient. It's like super, super efficient, because like you consider how many points the vertex shader has to calculate things on. It's way less than the number of fragments, because it's just the number of verts in the scene. So you could calculate the lighting per verts, and then lighting per verts. I really like lighting. You can calculate lighting per vertice. That doesn't actually sound any better. Anyway, and then just linear interpolate those lighting calculations across the triangles. So there's an interesting thing. We could talk about that a little bit on Wednesday, because it could be interesting to look at in terms of how diffuse lighting can probably just go across vertices, but then specular lighting gets weird. People love ray tracing. They're doing their lighting per vert. That doesn't even make sense. It's the opposite. Ray tracing doesn't work on vertices. Anyway. Alright, I'm not seeing any questions, so I'm not sure if people are hanging out waiting to ask questions or not. Probably not. So I may wrap it up here. I'll just, in a second, I will just wait a second or two. So if anyone's got any last minute questions, ask them now and I'll answer them. Otherwise, I will sign off. And I can understand maybe not too many questions, because we're still only halfway through the algorithm. I wonder if I can dig back into my chocolate yet. It's Kaichi's still laughing about the perverts thing. I have to be really careful when I'm saying that. I mean, like, there's always like, I always just assume that if I'm lecturing, well, at some point, someone's clipping a really specific part of what I say, and it's just going to go completely out of context like that. Logan saying, assignment 2, how should I create an object file if I want to do a complex 3D model? Simon said Blender. If you want to, you can make your own, but there are actually other places you can find whatchamacallit, royalty-free 3D models. There's a place called Turbo Squid, which is just a big collection of 3D models where you can let's get an elephant. You can take these 3D models. I mean, be careful. Not all of these are gonna work that easily with our the object loaders that we have, but heaps of these. Let's actually, like, where's the price? Free? And there's some models here. Why is this one in free? It's $164. Anyway, there's other ones that you can get, and you can take these models and put them in. Just be careful, because like lots of different models are in different formats, different kinds of layouts and stuff, so not everything's going to just work out of the box. Even at a professional level, using stuff like I've worked on projects where we grab a bunch of stuff from Turbo Squid, and we've got to kind of be careful. It's like, can we just drop this in, or do we need one of our artists to actually pull this thing into Maya or 3ds Max, redo everything in it, put it back into the format we use, and then send it over to us in the engine, right? So it's not simple. It's not just a one and done. Not everything in this shop is just going to go into your assignment easily, especially because our assignment is like all custom code as well. So it's not like some of these is going to be like, drop this into Unity, it will work immediately. Drop this into Unreal, it'll work. But ours, being a custom engine in a sense, is not going to have the same kind of requirements as those engines. So it's hard to say whether everything works. But you'll probably be able to find something on this site that's going to work. Pretty sure that's how Tutorial 5 is, right, Simon? You just found something on this site and like found one that was going to work with the importer that we used and dropped it in. So it can be a bit of trial and error, but it'll totally work. We'll see elephants in like every assignment. Get a rigged one and run its animations. Okay, that's a lot harder, by the way. But if you want to, hey, people put a lot of effort into those into the assignment 1 subjective marks. So someone had a rigged animated elephant, like that's worth a fair bit. Though that's not the only idea you could use. Dong's just asking, wait, how do you import the models into the program? So we actually have the model importer, and oh yeah, Simon's saying maybe filter by format as well in Turbo Squid. I've already left it. Yeah, and so it was like and so I was asking, will we cover how to load animations? No, we haven't, and it's kind of like it's just enough outside of the core kind of push for graphics that that we didn't do it. Like, it was enough that I was going to mention it, that it exists, talk theoretically about the techniques, but like when I think about what needs to go into each of the tutorials, there wasn't really time to do that one in a practical manner. However, funny conversation there between yourself and Simon was like, ask your tutor and they can help you out with it. And then like, wait, no, ask him anyway. Like, you can have a conversation about it, you know? But it might also be, this is quite hard. It might be something that's interesting. You can look it up in your spare time, and it might be a really cool thing to throw in assignment 3. Because if you have a rigged skeleton skinned animation model running, that's the kind of thing that would earn you like a really significant amount of marks in assignment 3. But I don't know, like, I haven't built one of those from scratch in a long time, but I know it's possible. So it's something that can be done. It's not super hard. And it might actually involve different model loading libraries and stuff, so it could get really finicky. That's why it's not necessarily going to be like, you know, core part of the course to do. Okay, Richie Lee says, if there are multiple light sources, how would the diffuse light calculate? Well, it calculates per light source. I'm going to do this on Wednesday, by the way. I'll do it on Wednesday, don't worry. But yeah, it'll calculate a separate amount of light per light source and add them together. So, if we go back to the maths, this symbol here is the sum of all of these for each of the lights. So, this symbol, is that a sigma? I think it's a sigma, is the symbol for like for each, you know, this is a for loop here. So this is a mathematical rendering of a for loop that goes across all the lights. So for each light, calculate this, and they're just going to be added together. So the more lights you have in the scene, the more chance you have of just like overlighting everything, and then your light values overflow over over 1.0. And it's like, yeah, it would be awesome. Yeah, animation's awesome. It's heaps of fun. I think it's like, it's one of those things that like, I definitely did heaps of animation when I was doing, like when we went past the course. So from like in the graphics course, your animation's usually like object animation. So we take the solid object and we move it around. Or even better, we take solid objects and we put them in a matrix hierarchy. We can move some of them and not others, and it looks cool. You know, so you can do robots and stuff like that. But once you have flexible things and you want to morph the model using like skeletal animation and stuff like that, it just gets a lot more complicated. So that's the kind of thing that I would do for something like, you know, advanced graphics or something like that. We'd actually implement the skeletal animation and things like that. But I think the introductory graphics, it's a little too much to try to learn. Like as it is, this lighting stuff that I'm doing is like 1990s. You know, it was state of the art in the 90s. So I would love to go deeper. Like, oh, you could do an entire course just on lighting. You know, there's so many different interesting lighting things. So it's like a course as long as this one on lights and shadows. You know, so there's like lighting, full screen lighting effects, ambient occlusion. And we get into like even anti-aliasing and stuff like that. And there's like light refraction. Just all this really cool stuff. But we're not going to get to nearly any of that. I have like the planned out for how long the course is going to be to get you this basic lighting equation, and then we hit the end of the course and I'm just like, I really wanted to do more. I wanted to do like post-processing and like and stuff like that, but I'm just like, we'll get there a little bit. But there's other stuff that we're going to do. So yeah, every little thing that I show you in this course, treat this course like an introductory course. Every little thing I show you in this course has a massive field to extend further in. So whether it is animation, massive field, lighting, even bigger, lots and lots of different things, modeling and geometry, heaps of stuff there, right? So it's like everything is like, yeah, I intentionally have to present something to you and then just kind of cut off at some point and go, I wish, but I can't teach you this next bit, you know, because everything I still want to teach you enough so that you can see the breadth of what's in graphics. We are going to do one or two advanced things at the end though, reflections and stuff like that, which are cool. Yeah. Oh wait, and you're using Maya, or so you're actually building your own models. So you build it in Maya, rig it, and put animations on it. That's gonna take you some time as well. If you could manage to get that into the scene, that would be pretty awesome. But don't kill yourself over that, right? It's a lot of work, and it won't, like, again, everyone puts a whole lot of work in for this final 10% in the assignment. If you want to, it's very cool, but no pressure, you know. All right, I might wrap it up there. Thank you everyone for hanging out. Wednesday we will continue. Someone who was asking, Richie said, yeah, multiple light sources. I definitely plan to cover multiple light sources on Wednesday as well, so we're going to look into that. Alrighty. Oh, you're doing 3D for another course. That's perfect. Yeah, if you could put them all together, that would be really cool. Because you could bring that to both courses. You can be like, I'm doing this other course where we built an engine, and here's my model in that engine. And then in this course, you can be like, well, I built a 3D model in another course, and now it's in it's in my assignment here, so I think that could be really cool. But again, yeah, as I said, don't. Within reason. Do the stuff that you need to do to get your marks, and then if you've got extra time, you can try to do that, like Voltroning your subjects together into one big thing. It's like a thesis, really. Like a thesis is like a Voltron of multiple courses stuck together into one big robot. Sometimes it literally is a robot as well. Okay, wrapping it up there. Thank you all, and I will see you again on Wednesday, where we're going to continue the algorithm and add in a bunch more details. All right, see you later.